we're going to do the graph. This is going to have a separate title. It's going to be the graph when it goes up there. This is not going to be something you're going to do directly on the test, but it is a good idea for you to practice drawing this graph and do it on your scratch paper. It'll really help you answer some of the true-false questions and some of the other questions that we have on problem 1. More easily understood, and more importantly, it'll help you to understand how and why things are stable in water and what's going to happen when we start doing constructing electrolytic cells in aqueous solutions. You can't understand it without this graph. So, although it's not explicitly on the test, it's a good idea to be able to construct it. You just derived the equations you needed for it. And always do it that way. Solve those equations. Go all the way back on your own. Do it from the Gibbs free energy, derive the Nuernst equation, find the appropriate form for that particular problem, the log form, log base 10, and now we can draw the graph. Okay. You're going to want to leave the vertical scale, which is potential. The vertical scale, which is potential, you want to leave enough room for at least 3 divisions up, maybe actually 4 divisions up, because this will be 0.4 volts, 0.8 volts, and 1.2 volts. This would be 4, and this would be 1.6 volts. So you should go at least that high above and minus 0.4 volts. So this should give us a good starting point. Now recall the equations were that we start with the original, what's the reduction potential of oxygen again? 1.2 what? 1? Yeah, 1.23. Yeah. So I go up at 1.23 volts, which is 1.23 volts. And it's going to come down about 0.414 volts by the time it reaches a pH of 7. And the pH scale should go from 0 to 14 out here. And it comes down about 0.414 volts, and then it actually ends up at around 0.414 volts at pH 14. So that's going to be and then it comes down an equal amount going below it comes down about 0.414 volts, so it's around 0.828 down this. Those should be sort of parallel-ish, okay? And this process is going to be commensurate with, this is the hydrogen couple, and that is going to occur at which electrode in the electrolytic cell?
Which one are you talking about?
The hydrogen, which is produced. So it's going to be, this is the cathode. And obviously this is the anode. So I have my cathodic process, my anodic process. And how do you remember that? What happens at which electrode? What is it called? It's an ox and a red cat. I know, it's kind of lame, but it helps. Okay, so now the reaction that occurs at the cathode is reduction. Okay. And so what occurs at the anode is going to be the opposite. It's going to be oxidation, and we oxidize water. And so we're going to have to write it as an oxidation, which is the reaction we wrote for the oxygen process in reverse. That reflects both of those reactions. And let's just point out a couple of features of this for a later reference. There is, for the reactions that occur between, for example, a metal when placed in water, when we're considering the stability of water, there is a kinetic barrier for those processes. And it's going to require a driving force in addition to the driving force for the voltage. And we call that overpotential, right? Does anybody remember what the overpotential is for water? 0.6 volts. And we give it the symbol eta. So I will do that in red at minus 0.6 volts, which is right here. So there's the overpotential.
What is that thing called again?
Eta. It's the Greek symbol. It's an N with a long nose. And So that represents the overpotential needed to surmount the kinetic barrier for all the processes involving solvent. And since that's what we're talking about, when is water going to be either a reducing agent or an oxidizing agent for a particular material? Like, for example, sodium. What happens to sodium? What's the fate of sodium when we toss it in water? What does it do? Yeah, it's oxidized. And so, the sodium is converted to sodium plus sodium ions, and it gives up its electrons, and what happens to the water?
Covers varsity.
Well, yeah, but the water is going to be reduced. So, in other words, water is going to be reduced. So, we're interested in this cathodic process. This is going to occur whenever the reduction potential for the solvent, water, is greater than that of the reduction potential for a given metal. And if we take that into account, we would expect the reduction potential for zinc, which is minus 0.76 volts, 676, it's right around here, minus 0.76 volts. Well, that is a flat line. So I know that zinc is going to be reduced at a potential of zinc plus 2 ions going to be reduced at a potential of minus 0.76 volts, which means it has, since its reduction potential lies below that of the solvent, we would expect right up front for zinc not to be stable in water, because the water it would be reduced by zinc, by the reduced form of the zinc couple. E non. So we represent it as this is the oxidized form on the left and reduced form on the right. The reduced form of zinc should will be oxidized by the solvent because it has a lower potential. But when I place zinc in water, it doesn't give off any hydrogen bubbles. It just sits, it sinks to the bottom and it sits there. As long as, and that's why we have zincs on the backs of our boats. We use zinc plates as a sacrificial anode to protect the boat from electrolytic damage because it's in an electrolyte like salt water. And that you see them down there on the back of the boat on the transom, and you don't see any hydrogen bubbles coming off. You put on a set of zincs, they last about 6 months to a year, depending on what type of conditions are there. So it's not like the reaction is that slow. It is robust enough. If it wasn't for the other processes that are going on, the zinc would be robust in water at pH 7. So because of the overpotential, zinc is stable in water at pH 7. It's above this line. When it has to get, it doesn't go below the line until a pH of around 3. You can see where it intersects this line. At around 3, it now is unstable with respect to being oxidized by the solvent. Water will oxidize zinc at a pH less than 3. So you drop a piece of zinc, and you've all done this. You drop a piece of zinc in acid, you see bubbles coming off, all kinds of active things, and the zinc gradually dissolves into zinc ions. This is easily understood now. And once we understand the oxidation and the reduction of water itself, and the pH dependence of it, and the overpotential for the solvent.